Okay, any thoughts? Which one should be the most crystalline? Anybody? Yeah, what do you think?
Syndiotactic. The second one.
The second one's your best guess. Any thoughts why?
It looks like it can link in not just end to end, but.
Ah, okay. If these things had an extra bond that could come off the side, right? Then I see what you're meaning. That would definitely give you a more three-dimensionally bonded structure, which you're interpreting as crystallinity. When we're talking about crystallinity with polymers, what we're really talking about is these things are chains. How well do they actually stack together and start to look like a solid, as opposed to being a bowl of spaghetti, right? So of these three, if you want them to stack next to one another, isotactic, meaning that they're all on one side, is going to be the best for these things to stack together because it'll bring them closer together. Because imagine you've got things on both sides. If you've got these benzene groups on both sides, you can have them bonking into each other, right? Like this scenario right there, where they're now overlapping with one another. We call that steric hindrance, right? It's atoms just basically just pushing into one another, and that pushes the chains further apart. If the chains are further apart, there's less van der Waals forces between the chains, and they're less tightly bound, right? So you actually would want them on the same side to increase crystallinity. Then you can also have geometric isomerism. So for example, if you have a double bond, that's one that's not going to rotate, it's going to be fixed. You can have your side groups on the same side, which we call cis, or you can have them on opposite sides, which we call trans, right? So these are the different sort of terminology. So if you hear polymers, they say it's atactic, isotactic, cis, trans. What they're describing is how these mer units are coming together. Okay. Okay, let's talk about thermoplastic versus thermosets. I think we said this before, but a polymer, there's really two camps of polymers. You have your thermoplastics, which when you heat them up, you overcome the van der Waals forces holding the chains together, and it melts, right? And because those are weak van der Waals forces, they melt at low temperatures compared to metals or ceramics. You can also have thermosets, though. A thermoset is something that has significant covalent bonding between the chains, either through cross-linking or through just a three-dimensionally structured polymer. Those, if you heat them up, you're not just going to have a little bit of heat necessary to overcome the van der Waals forces. You're going to have to add enough heat that you actually break covalent bonds, and by that point, it won't just heat up and melt. It's probably going to heat up and burn. So if you've ever taken rubber, if it's vulcanized, if it's been cross-linked, it won't just melt. It's actually going to burn. Okay. Okay, you've got copolymers again. So let's say that your repeating unit is a polyethylene. That's the C2H4 repeating unit. But you could have that, and then you could have something else. So we saw this with the Cheetos and the hot dog demo last time. You can have lots of different mers that come together. And a lot of actually the rubbers that are used in like bumpers and stuff. So if you ever hear like ABS rubber, those A, B, and S stand for different mer units that are in the main chain, right? In that case, I think I've got 3 different ones. So it doesn't have to be 1, doesn't have to be 2, it can be many different mer units that come together to make this. And so increasingly, the field of polymers is becoming so interesting because you can have so many different blends of these monomers. You can have 5 or 6 or 7 different ones, and they can be all along the chain alternating. They can be random, right? So if it's alternating, that's a copolymer that we say is, sorry, what do you call that? We call that alternating. If it's random, it's random. If it's blocked, then you have blocks of them at a time, right? Or you can have graft, where the different mer actually isn't even on the chain. It sticks off to the side, right? So you have lots and lots of abilities to modify your polymer structures because these can go in lots of different places. And so the field of material science that works in polymers, a lot of it is focused on how do you manufacture polymers that have the exact polymer chain, dimensions and shape that you're looking for. Okay, polymer crystallinity, we've mentioned that they can actually become kind of crystalline. The more entangled they get, the lower the crystallinity. I think we've already talked about that. How about this? Would you expect higher or lower density in a crystalline or amorphous polymer? Maybe turn to a neighbor and discuss this for a second. Okay, what do you think? Amorphous or crystalline should have a higher density? Crystalline should have a higher density somebody's voting for. Well, let's compare. This is quartz and glass, right? The one on the left we say is crystalline, right? Because it's a regular repeating structure. The one on the right is amorphous. And if you just look at it, the one on the left is more densely packed. It's perfect every atom's location. The one on the right has some poorly utilized space, right? You could have put another maybe in the middle of that, but it's not using its space correctly. So the same thing happens in polymers. If you have an amorphous versus a crystalline polymer, the crystalline one will be more dense, right? So when you're trying to calculate polymer crystallinity, one of the great tools that we have is using density, right? So here's how it works. The percent crystallinity of a polymer is going to be equal to the density of a completely crystalline sample multiplied by the your sample minus an amorphous density, right? So you have to know these values ahead of time. You'd have to know ahead of time what is an amorphous polymer's density and what is a completely crystalline polymer's density. If you have the amorphous and crystalline, then you can measure the density of your sample. So S is sample. And from those three values, you can calculate what percent crystallinity your polymer is, which is a pretty cool tool. So you can look up the crystalline and the amorphous values in literature. Oftentimes those are reported in literature. You can measure your density of your polymer and you can say, oh, it must be 40% dense or 80 or whatever the number is, okay? All right, if you slow cool your polymer through the melting point, so let's say it's molten, it's a thermoplastic, and you slowly cool it down, you're gonna give it more time at a higher temperature. The more time at a higher temperature it has, the more it's going to be able to find its lowest energy configuration, which is gonna be more crystalline. The polymer chains are gonna line up better. So you tend to get better crystallinity if you cool it down slowly. If you want a polymer that's amorphous, you would cool it down a little more quickly. Again, if you have lots of side groups, you're never gonna get it perfectly crystalline. That's always gonna reduce your crystallinity. If you have, we have talked about atactic versus iso or syndiotactic. So I think we're good. The last thing to talk about is that even when it does crystallize, you're only ever really crystallizing a section of it at a time, right? So if you look in the book, they have a section where they talk about the micelle model. This has been updated over the years. There's still some debate about what the crystalline structure of polymers are, but people tend to agree in the following, that there are regions of it where the chains line up. And the way that they line up is probably by zigging back and forth, right? So you have some region where the chains zig back and forth. And if you look at this, you could actually assign this some sort of like crystal structure, right? You could assign like lattice parameters to this, and you could count how many mers there are per unit cell, which is what we can do. We can do X-ray diffraction on these, and some of them you'll actually see X-ray diffraction peaks because regions of it do line up. Then they've got interplanar spacings that causes diffraction, so you can do diffraction on some of them. Other ones which don't crystallize very well, if you put them in an X-ray diffractometer, all you'll see is this. Again, plotting intensity versus 2 theta. You'll see what's called an amorphous bump instead of sharp peaks. And in some materials, you'll see a little bit of both. You'll have a peak or two, but mostly this amorphous background, just sort of this big broad bump there. Because again, polymers, you'll have regions of crystallinity and then you'll have amorphous regions kind of collecting those. So if you hear people discuss spherulites of polymers, they're talking about the overall polymer, which includes both crystalline and amorphous regions. There's some evidence to suggest that these things grow radially outwards, so they're kind of beads-shaped things. I think that's all we have to say about polymers. Any questions I can answer about polymers before we move on? Okay, let's keep going then. So the next chapter that we're talking about is now imperfections. We've described thermodynamics, we've described phase diagrams, we've talked about crystal structures and polymer structures, but everything's been sort of perfect, right? In thermodynamics, we assume that things reach thermodynamics. We haven't talked about kinetics yet. In crystal structures, we drew these things, but we assumed all the atoms were in the spots where they're supposed to. So what happens when the atoms are not in the spots where they're supposed to, right? That's imperfections in it. So this class, our learning objectives are first to talk about zero-dimensional defects. These are called point defects, which is either a vacancy or an extra atom. We'll then talk about how to take into account charge neutrality with such defects. We'll talk about thermal expansion and how it relates to the vacancy formation in lattices. And then maybe we'll get to some important alloys before we're out of time. So let's see. Our zero-dimensional point defects, 0D point defects, right? In metals, these are either going to be vacancies or self-interstitials, right? So you've got your atoms in some sort of arrangement, and instead of being perfect, you've got this atom out of spot, right? So that would be an example of a self-interstitial. And if this atom came from right there and it moved to over there, then this is two different point defects. You have a vacancy and a self-interstitial, right? It doesn't have to be that way. You could have, say, an iron lattice, and in the iron lattice, you have now a different atom, like carbon, occupying an interstitial site, right? So this is now steel. As soon as you start to put carbon into iron, you've created steel, but it's occupying an interstitial site. And to figure out exactly where that interstitial site is, we'd have to pull up the crystal structure for whatever iron crystallizes into and see where the open spots are, right? Okay, so that's vacancies and interstitials, and basically these things are everywhere. You can't get away from them, right? So let me ask you this, unless it's already there. Yeah, what's driving it, right? What is driving this? Why can we not get away from vacancies? Why will they always be there? So turn to a neighbor and discuss what is the, think thermodynamics, reason for why this thing wants to be there. Okay, what do people think? What is our thermodynamic reason that vacancies want to form? Anybody have a thought? What do you think, Elise? Absolutely, right? Imagine that where atoms are located, let me switch back to red. If you've got atoms each there, that's a very organized, ordered lattice. And if you want to make it more disordered, you would just get rid of something, right? That has become more disordered, right? Because this vacancy, it could be there, it could be there, it could move around, right? So that's a more disordered lattice. So entropy is driving this forward. Entropy drives the formation of vacancies. So if entropy is always going to increase as long as you're adding these things up to a point, why will it ever stop? So what's preventing this, right? What's preventing vacancy formation? Yeah, Spencer? How come? You're right. Yeah, you're getting there, Rosa.
It leaves bonds.
It leaves dangling bonds, right? All these things want to be bonded to one another. Now those are all missing bonds, right? These things are all happy. They've got bonds. They're delighted. You leave dangling bonds, right? So this is entropy versus enthalpy. This is the classic thing that we've been fighting with, right? Gibbs free energy, G, equals H minus TS, right? H is your enthalpy. That basically, in this class, think of that largely having to do with bonds, right? Bonding. Whereas S is going to be largely disorder, right? So on one hand, you increase you can lower the free energy because you increase energy, right? This is a negative term. So free energy can go down if you increase your degree of disorder, but it's going to cost you in terms of H if you go too far, right? So you're going to form some vacancies. So how many form? The way that we can calculate this is by using the activation energy for vacancy formation, right? So NV, that's the number of vacancies at equilibrium. Again, this is assuming that we reach equilibrium, which means high temperatures, long times, right? That's equal to N, which is the total number of atomic sites multiplied by the exponential of negative Q sub V, our activation energy for vacancy formation, divided by KT. Okay? So why is this not RT instead of, why is this KT instead of RT? The reason why is because we're now talking about an event that happens on a per atom basis. If you talked about creep, that's happening to an entire mole of substance, not an individual atom. When you talk about things that happen on per atom, the energies involved are way smaller, so it makes sense to use a smaller constant here. So we use Boltzmann constant rather than the gas constant, okay? So the activation energy basically dictates how many vacancies exist at any given time. If your activation energy is really small, then you're going to have more values because this is exponential of a large negative number, okay? Okay, any questions on this, on using this expression? So if you wanted the fraction, actually maybe that's this next question. Yeah, how about this? So let's do this one, and our clickers are not working until I get my laptop back. But for copper, the activation energy for copper is 1 electron volt. That's for vacancy formation. So what would be the vacancy concentration at 800 Kelvin? Okay, vacancy concentration, that's just going to be the number of vacancies divided by the total number of sites. That's a concentration, right? So all we do is we brought the N over, right? Plug that in. So what are you guys getting? Plug that in. Anybody? Yeah, I'm getting the same thing. So that is a very, very small number, right? So just to frame of reference, that activation energy for the vacancy formation is pretty small. 1 electron volt's that's not a huge number as things go, and yet we're still finding that only 5.03 times 10 to the negative 7, right, is our fraction of vacant sites. So even though vacancies always happen and there's this thermodynamic reason for them to be there, we're not typically talking about all that many, right? It's a pretty small number. So again, if I told you, actually how about this? How would you answer this question? Per centimeter cubed, how many vacancies are there? Right, you figured out the concentration. How many vacancies, so turn to a neighbor and work this one out. How many vacancies are there per cubic centimeter? What else would you need to know to answer that question? Okay, anybody have a thought? What do you need to know? There's one fact that we need to know to answer this question. Yeah.
Vacancy sites per cubic centimeter. So.
Okay, how do we get there? What info do I need to give you guys so you can solve this? You need the density of copper. What is the density of copper? 8 or something? What is it? Somebody have it? Let's look it up. So the density of copper is, have no fear, we prepared a contingency plan for just this very thing with my loaner laptop. Okay, the density of copper is 8.96 grams per centimeter cubed, okay? So given that the density of copper equals 8.96 grams per centimeter cubed, how are you going to go about solving this question? What's the right approach here? You're trying to figure out how many vacancies there must be per centimeter cubed. Yeah, Elise?
Can we calculate the theoretical, I guess, mass, like the one?
Yeah, let's go back to copper in its lattice, which I think we already showed you guys. Copper is face-centered cubic, right? So the theoretical density of copper should be the number of atoms. How many atoms are there per unit cell in FCC? 4, multiplied by the mass of copper, which is 63.54, is that it? That sounds right-ish. 63.54, is that right? 546 grams per mole. This is divided by, we need to know the volume or unit cells, we need the lattice parameter. which for copper is 3.597 angstroms. We cube that and we multiply by Avogadro's number. So our per moles cancel out. Okay, so let's actually talk about conversions real quick. How many, if I want to compare this to something per centimeters cubed, how do I need to go from angstroms cubed to centimeters cubed? There are 1 times 10 to the 8th angstroms per centimeter, and then you need to cube that, right? So basically 3.597 angstroms cubed. You could say that there is 1 times 10 to the negative 8 angstroms per centimeter, and then you just cube this whole thing, right? And that will give you angstroms or centimeters cubed. So you're going to divide it by 1 e to the negative 8 cubed. Okay? What's our next step? So then you've got density. All right, that's kind of helpful maybe. What's the next step? Yeah, Josh?
So I want to go from grams to centimeter cubed to atoms per centimeter cubed.
That's exactly right. Yeah. So maybe this is a good point for you to take a stab at this. You want to take Josh's advice. Go from grams per centimeter cubed to atoms per centimeter cubed. And then you know how many atoms there should be per cubic centimeter. And then, right, figure out how many, you know the fraction of them missing, so you can figure out how many atoms are missing. So give that a shot. Maybe try working that out. By the way, if you just compare the density of actual copper versus its theoretical density, you see this difference, right? It's 8.96 when you actually buy copper from wherever, but it should be, if all the atoms were in their occupied spots, it should be 9.06, right? So they're shipping you, right, this copper. You're actually getting a little bit stolen. You're not getting all those copper atoms that you want to get because there's vacancies and you can't get away from it. So you see evidence of that, but you need to get to how many there are, right? So Josh had the right idea. You want to go from grams per cubic centimeter of your compound to number of atoms, right? So how do you do that? Like, this is what it should be, right? That's how many grams per cubic centimeter. We can turn that into number of atoms. How? Use the molar mass, right? So let's do that. Let's give ourselves some more space. It should be 9.06 grams per cubic centimeter, right? We want to turn that into atoms, right? So first we go to moles. We say that there are, what was it, 63.546 grams per 1 mole of copper. How many atoms are there per mole of copper? There are Avogadro's number of them. So now you've got the number of atoms per cubic centimeter by doing that. Okay, so what does that come out to? 8.58 times 10 to the 22nd, did you say? Somebody else getting that? So that's the number of atom sites, right, per centimeter cube here, right? Everybody following so far? And then we know the fraction of sites that are vacancies. We just solved that previously up here. We said that is NV divided by N, right? So right down here, this equals N, right? So if you want to figure out the number of vacancies, you're going to say that, okay, NV over N equals, what was it? 5.03 times 10 to the negative 7. Oh dear. Yeah, you're going to solve for NV. 5.03 times 10 to the negative 7. Solve for NV and you get, what are we getting? .31 times 10 to the 7? 16. Times 10 to the 16. So that's how many vacancies there are per cubic centimeter. So even though it's a small fraction of the sites occupied, there's just a gazillion, atoms per cubic centimeter. So you're still talking about a large number of vacancies. It's just a small fraction of vacancies, okay? Rob, we'll do last question.
Would you be able to compare the theoretical with the actual potential of both the atoms and then just subtract the two?
Yeah, that would give you, in fact, that would be one way to estimate the activation energy of vacancies. We'll start there next time. Okay.